Hello friends, I welcome you in lecture number 9 on complex integration. In this lecture we are going to discuss one problem which was asked in GTU Summer 2021 examination. So let's try to evaluate this complex integral. Here function is real part of z square and we have to find out integral of this function along this contour, which is the boundary of this square with vertices 0, I, 1 plus I and 1, and in the counterclockwise direction. So first we write down given function and we denote function by f of z. So let f of z equal to real part of z square, and if we take z equal to x plus iy, then z square will be equal to square of x plus iy, and if we simplify this we have z square equal to x square plus 2ixy plus I square y square, and because I square is minus 1 we have this x square minus y square plus I times 2xy, and we are interested in the real part of z square. So therefore f of z equal to real part of z square, and the real part of z square is x square minus y square. So our function is x square minus y square. Therefore f of z is x square minus y square. Now we see what is given contour. Given contour is the boundary of the square with vertices 0, I, 1 plus I and 1. So first we sketch this square with given vertices. So for example, this is the xy plane and we have a square with vertices. Our curve is this square with vertices. First we write down what are the vertices. Vertices are 0, I, suppose this distance is 1, then this point is I, and if this distance is 1, then this point is 1 plus I, and this is 1. So we join all these vertices and we obtain the square which is our contour. So this is the square with vertices 0, I, 1 and 1 plus I. Now we have to consider boundary of this square in the counterclockwise direction. So suppose we start from 0, then we have this direction which is counterclockwise direction, and this is x-axis, and on x-axis value of y is 0. This is y-axis, and on y-axis we know that x is 0. So our curve is boundary of this square, and we can see that our curve has not a single equation along this boundary, because we know that if we consider this portion, then representation of this portion is y equal to 0, okay, because it is on x-axis. If we consider this part, then along this part value of x is constant 1. So here we have this equation x equal to 1. Similarly, if we consider this line segment, then at all points on this line segment value of y is 1. So equation for this line segment is y equal to 1, and same thing here, this is on y axis, so here we have x equal to 0. So our curve or our contour C has not a single equation, because here in different parts or in different sides of this square representation of contour is different. Along this path y is 0, along this path x is 1. So what we can do is we can divide our contour into 4 sub contours: C1, C2, C3 and C4. So suppose this is C1, this one is C2, this is C3 and this one is C4. So along C1 y is 0, along C2 x is 1, along C3 y is 1 and along C4 x equal to 0. Or we can write down all these contours here separately. Representation of C1 is y equal to 0, and we can see along C1 y becomes constant and x is changing. So x is changing from x equal to 0 to x equal to 1. So here we write that x lies between 0 and 1. Similarly, along C2, if we observe this line segment, then along this line segment x becomes constant and y is changing. So at this point value of y is 0. This point we can write as 1 0, this we can write as 1 comma 1. So at this point value of y is 0 and at this point value of y is 1. So y is changing from 0 to 1 along C2. Similarly, we can represent C3. Along C3 y becomes constant, y is 1 and x is changing, but direction is counterclockwise direction. So we are going from this point to this point. At this point value of x is 1, so lower limit for x is 1, and this we can rewrite as order pair 0 1. So at this point value of x is 0, so x is from x equal to 1 to x equal to 0 along C3. And along C4, we are on y-axis. On y-axis x is 0 and we are going in this direction, so y is changing in this direction. Now at this point value of y is 1, at this point value of y is 0, so y is from 1 to 0. So given contour is boundary of this square with these 4 vertices, and that contour we have subdivided, or we have written that contour as union of these 4 contours C1, C2, C3 and C4. So integral along this contour will be equal to sum of integrals along C1, C2, C3 and C4. Now we have f of z equal to x square minus y square, and we have to decide value of dz along each of these contours. So we know that if z is x plus iy, or we can write here if z is x plus iy, if we consider any z along C1, then z is x plus iy, but along C1 value of y is 0. So along C1 z will be x, therefore dz by dx will be 1, and we will write dz equal to dx along C1. If we take any point on this part along C1, then z is x plus iy, value of y is 0 along C1, so we put y equal to 0, so that we obtain z equal to x. And if we differentiate z with respect to x, we obtain 1. Therefore we will write dz equal to dx along C1. Similarly, we have to decide all these things along different contours. Now along C2 x is 1. So if we take any point z along C2, then we have x equal to 1. So we have z equal to x plus iy. We put x equal to 1 and z becomes function of y, 1 plus iy. So if we differentiate z with respect to y, we have dz by dy equal to derivative of 1, which is 0, I into derivative of y, which is 1. So along C2 dz will be equal to I times dy. So here I write directly dz equal to I times dy along C2. So we have to take care of all these little things. Same thing for C3. Along C3 y is 1 and x is changing, So z will be equal to x plus iy. We put y equal to 1, so we have x plus I, and if we differentiate with respect to x, dz by dx will be 1. So along C3 we will write dz equal to dx, and along C4 x is 0, so z is x plus iy. X is 0, so we have iy, and if we differentiate with respect to y, dz by dy is I, so dz will be replaced by I dy along C4. So now we consider all these things in our mind, and we try to convert our contour integral, a real part of z square dz, in terms of either x or y. Now integral along contour C is equal to integral of our function is real part of z square dz. Now real part of z square, as we have simplified, is x square minus y square integral along contour C. Now this is equal to integral along C1 of x square minus y square plus integral along C2 of x square minus y square with respect to z. Similarly, integral of x square minus y square along C3 and integral of x square minus y square along C4. Now we use different parameterizations along these different contours. So along C1, first we observe what is constant along C1. So along C1 y is 0 and x is changing from 0 to 1. So we put y equal to 0 in x square minus y square. So we have x square, and x is changing from 0 to 1. So along C1 I am using this information. I put y equal to 0, limits of x are from 0 to 1, and I will replace dz by dx. So here I write dx, dz equal to dx along C1 y is 0, so x square minus y square becomes x square, and x is from 0 to 1. So now we write what we have along C2. Now along C2 x is 1. Okay, now we are using this information. We put x equal to 1, y is changing from 0 to 1, and dz is I dy. So x is 1 along C2, so x square is 1 minus y square, and y is changing from 0 to 1, and dz is I dy along C2. Let me check again. Along C2 x is 1, y is from 0 to 1, and dz is I dy. So that I have written correctly. I have taken x equal to 1, dz is I dy, y is changing from 0 to 1. Same thing we do for C3 and C4. So along C3 y is 1, x has limits from 1 to 0, and dz is dx. So along C3 y is 1, dz is dx, and x is changing from 1 to 0. So let me check again. Y is 1, x is from 1 to 0, dz is dx. So we put y equal to 1. So y square is 1, dz is dx, and x is from 1 to 0. And finally we use information of C4. Along C4 x is 0, y is from 1 to 0, and dz equal to I dy. So along C4 x is 0, so we have minus y square, y is from 1 to 0, and dz is I times dy. So now we can see that here integral is with respect to x, and we have function of x. Same thing here, integral is with respect to y, function of y. So we can easily do integrals here. So we consider now integrals. Integral of x square is x cube by 3. Limits are from x equal to 0 to x equal to 1. Here I is constant that we can take outside integral. Integral of 1 is y minus integral of y square is y cube by 3, and limits are from 0 to 1, plus integral of x square is x cube by 3 minus x, limits are from 1 to 0, and here we can take minus I outside, and integral of y square is y cube by 3, limits are from 1 to 0. Now we put limits. In first part x is 1, upper limit is x equal to 1 minus lower limit is 0. So it is 1 by 3 minus 0 plus I. Upper limit is 1, so we have 1 minus 1 by 3. Lower limit is 0 and we have y here, so it is 0. Plus in this upper limit is x equal to 0, so for x equal to 0 we have 0 minus let me write this bracket, and we put x equal to 1, so we have 1 by 3 minus 1, and minus upper limit is y equal to 0, so we have 0 minus 1 by 3. Now we simplify all these things. This is 1 by 3 plus this we can write as 3 minus 1, 2 by 3, so 2i divided by 3. Same thing here, this is going to be minus 1 by 3. If we take negative sign inside the bracket, minus 1 by 3 plus 1, and here negative positive, plus I divided by 3. So here 1 by 3 will cancel out, and we have this 1 plus 2i by 3 plus I by 3, so that we can rewrite as 2i plus I divided by 3. So we have 3i divided by 3, and 3 will cancel out, and we have 1 plus I. So value of given contour integral is 1 plus I along the boundary of the square with given vertices. Okay, so in this way we can easily find out this type of complex integrals, but we have to take care. If our path has different equations in different parts of the xy plane, we have to use appropriately those different equations of different contours. So here given contour was a union of different contours whose equations were different, so we have used all those equations accordingly. Okay, so I hope this is understandable to you, and I hope you like this lecture. Thank you.